Hello, everyone, and welcome to another Clojure study group. My name is John Stevenson, and this week we're going to talk some more about Mariacloud, which is a really nice visual, interactive learning environment for Clojure. So last week we covered some of the basics, and this week we're going to go into some animation and some other fun things you can do with something called cells. Which is similar in concept to a Clojure atom. So we'll also have a quick look at Clojure atoms as well. And you can see how to safely manage state changes in Clojure using atoms and something called software transactional memory. What we can do here, let's share my screen. Everybody, there we go. And where do we get to? So in case you didn't see last week's video, this is Mariacloud, Maria.cloud, and we had a look at this learning Clojure with shapes exercise, and we were creating circles and squares and so on, and lots of basic stuff there, and it was a nice environment to get going and build a curriculum. So the idea is to build a curriculum for ClojureBridge. And so I'm doing that. Oops, not there. Yeah, so I'm starting to build up these ClojureBridge curriculums so we can use Mariacloud very easily in our next ClojureBridge environment, next ClojureBridge event. So we're going to cover some of these. And so the nice thing about Mariacloud is you can save your own copies to a GitHub gist. And it is just a ClojureScript file, and you just put in code, and then a text around it. You just put the text in comments, and it appears in the page just like this. So this text is just a comment, and you've just put Clojure code in as normal. Okay, so we're going to walk through some of the examples that they've done already in Gallery, and also explain how some of these things work. Some of these things are using this idea of cells. So we're going to show you what kind of like the what cell is and what the constraints are around it, and then also talk about Clojure atoms as well, because that's related. Okay, let's go and start playing. So I can just evaluate code with Control-Enter, and or I can do Control-Shift-Enter anywhere in the expression, and it will evaluate as well. So for Mac users, it'll be Command-Enter. And so this one is, we're using map. We're going to map a function over the results of mapping a function over range. So we've got this range of 0 to 250. With a step of 25. I think that's how range works, if I remember rightly. If we ever wanted to find out, we can always do doc range. If we evaluate that, then it'll give us the implementation for that function. So yeah, so it's taking, so with range, you can pass any number of, we can pass no arguments, which will just generate a lazy sequence of infinite integer numbers. We can just pass the end number. So if we did range 10, it would generate all the integer numbers up to 10, but not including 10. It's the end is exclusive. And we can do start and end. So we could do like 10 to 100. 1 to 2, and then we can also do start, end, and step. So here we're kind of just going to create every 25th. So like for this range one here, we're just creating every 25th number. Oh no, that's not the one I wanted. Here we go. We do range 0 to 5. And then we can see these are the numbers we're going to get. And there is, how many numbers of those are there? Boom. We've got the Slurpee numbers. There we go. Yeah, I was using Emacs to copy paste that. Doesn't look like. So that's the range of numbers we're going to create, and then there's 10 of those. So there should be 10 of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we got 10 numbers, 10 blocks, which matches how much the number we're generating with range. And so these are, I guess these are color values. Oh yeah, so we're feeding these into this HSL, which is this color. It's like RGB, but instead of red, green, blue, it's hue, saturation, and light. So it's just another way to represent colors with 3 different numbers. And so this is what we're doing here in the example. And so we're going to generate a bunch of numbers. Well, let's just show you what we're doing here. By the way, so we're generating all these things here, and basically generating these color values that we're going to use to represent all these different colors. And can we just do HSL? What does that do? Does that work? HSL itself. Oops. Don't forget the brackets. There we go. 0, 150. What does that actually give us? Oh, interesting. That's just returning a string, which is the color model that we're using. So we're using HSL to kind of define what the colors is, and these are the values of the colors that we're going to do. And then we can use this colorize feature. So we're going to generate a bunch of squares, and each square is going to take one of these HSL colors, and it's going to be mapped over the whole thing. So it generates all these nice squares. So it's quite neat. Cool. And colorize obviously uses this HSL color model for colorizing. I think it can use RGB as well. And so, yep. And here we're doing the same thing. We're just changing the S, so the saturation. So we're using the same color because it's color of 120, like the hue. I believe the hue is kind of like the main color. Yeah. So here we've got red. Oh yeah. So here we've got red as 0, and so 120 is green color, and we're saturating, and the saturation is what we're varying. So we're varying kind of like the amount of green that we're going to see in that square, and then if we also did the light, would kind of vary the lightness of the thing as well. Cool. Any questions? No questions so far. Okay. And there's just a whole bunch of different examples. So yeah, again, here's an example where we're changing the lightness of the green color. So we're keeping the color, the hue, and the saturation the same. We're just changing the lightness of each time. And there's just doing the same thing with RGB. Oh, and this time we're using circles as well. So we could use circles, use triangles from shapes. So that's how you do it. Oh, pretty. And yeah, so this RGB is just using different red, green, blue colors each time for that as well. And we do opacity and gradients as well. Yeah, that's creating a big block of gradients. So you can see all the different shades of gradients, so like going from one color to another in a nice graded pattern. And the opacity is just a value that we're passing in to colorize. So once we've colorized something, we can then change its opacity. So it can be again, it's a bit, I guess it's a bit like lightness, but more general. You should be able to apply that to either color, and it's just how much of that, how transparent it is really. If it's completely opaque, then you can just see the color. If it's quite a low opacity, then it becomes more transparent. And this is just so this is just taking the range again, and although it's quite a smaller range, and we're creating the triangles, and it's so we're not generating a range, we're just specifically specifying the blue color, and we're applying opacity from this range of numbers here. So so basically going from 0 to 1 in increments of 0.1. So opacity, in this case, we set it as opacity 0 would be transparent, which is why you can't see this first one, this first triangle. It's so that's got 0 opacity, so that's transparent, and the final one has, well, I assume that will have 0.9 opacity, so it's close. It's the full color more or less, with just 0.1 difference. And color gradient, we've looked at that. So this is just let's skip on to the next one. That's kind of similar. Okay. And this is using this is using position and rotate to move things around. Again, this is quite static. This is just kind of changing the position. We could kind of rotate it and keep the same position and just redraw it over, but then we need a mechanism to update the cell, which we haven't come to just yet. So this is basically just using, this is a threading macro. So it's basically saying we're going to map the range, the values we get from range, we're going to pass through into triangle, position, rotate, and colorize, and then return the results. And then we're just going to concatenize them all together in a white background. So we're putting them on a white background, and we're applying the layer to those as well. So we covered layer before in the last video. So layer just allows us to put one thing on top of them. So we can put all these triangles on top of the rectangle that we're creating here. Is that any difference? So this is kind of the same. We've got a much smaller position that we're moving from, and we're actually just rotating that way. So we're just making a bounding box. So we could, if we could animate this, that would be quite cool to see the box moving up and down, up and around. Minimal cell. Okay, and so this is what we got. So we start to use cell. So here we can see we're using this idea of cell to update the existing output. So we're effectively changing the state here. And so we're defining a cell, which is we're calling cell function on these arguments. So we're setting an interval of 250. So that's going to change every 250 milliseconds, I think. And we're using the function to basically colorize this square. So we define a square 50. We're going to colorize that using a random number. Palette, do we define palette somewhere? Maybe palette is defined somewhere. Saturday. Oh, it's up there, isn't it? I didn't see that. Oops, it's in the let. Oh yeah, so we're defining this palette of colors in the let. And so we've got red. These are the colors we're going to cycle through. So we could add another color in there as well. What's that going to happen? Oops. There we go. And yeah, so let's change it. So we can add colors in there and reevaluate and play around there. So it's, yeah, we can kind of get a nice progression of color changes there. Yeah, so the cell basically allows us to change the existing value in there. And so we're changing it by setting an interval of how often we want to change it. And then this function is what we're changing that content to. And this let statement is just is defining this local palette value for us. So we can kind of just, otherwise it would get a bit messy, which we'd have to expand this if we didn't have a local value. So that's a simple example of a cell. What do we got here? Oh, we're defining confetti. So here we're not using a cell. We're just generating confetti. But if we can kind of simulate what's going on by just reevaluating this over and over again, we can get some kind of fake animation there just by pressing Control Enter over and over again. So each time we evaluate it, it's going to redraw it, but obviously that's a bit, that's not really proper animation. So we can have another version where we can just wrap that in. So we've taken confetti that we were calling before. So confetti is just basically going to generate a bunch of colors. It's going to cycle through these colors. So rather than doing the random int, it's going to, it's not going to pick a random color. It's going to cycle through each color every time we get a palette. So when we call map colorized palette, it's going to get aqua and then spring green, then magenta, and then go back round again and round again and round again. And yeah, so this is just a loop that's going to be called once when we a thread that's going to be called once when we call confetti. But if we put that confetti inside a cell and give it an interval, then we can then animate that and save our cells pressing the Control Enter over and over again. What else if we do? Let's see. Slower. There we go. Yeah. So the bigger the number, the slower it gets, because obviously the interval is like now 1000 milliseconds. If we do 10 milliseconds, that's probably quite crazy. Eee! Yes, there we go. That's a lot of confetti. There we go. Something more sensible. Yeah, so every tenth of a second, so that's 100 milliseconds, which is a tenth of a second. So we don't have to explicitly put cell into something to animate it. We can wrap something around a cell and just get it to redraw over and over again, which is quite cool. And we can do things with cells. We can make them interactive as well. So here we've got this triangle that we've created where we're setting this shape size. We've created this size, initial size of a shape to be 16. And so we've got that's the value here, but we've done that in this def cell. So like we'd do def to define a name for a value. We can do def n to define a function. Here we're doing def cell, which is defining a cell. So it's defining a value, but this value can change, and we'll track the changes in shape size. And so we have the cell, which is going to generate some HTML for us. And so we're using this hiccup style code to generate the HTML. So rather than doing lots of angle brackets and typing in the actual HTML, we've got a function called HTML which will generate our HTML code for us, which means we can use specific Clojure data structures, and it's a bit easier to work with and manipulate and write functions around those. So if we want a div, a divider, rather than doing the angle brackets div, so rather than doing normally in HTML, you would do a div, and you close the angle bracket, and then you would do something else in here and some HTML in there, and you'd have a closing div. So, and the same thing, so you might do a h1 title, close that h1. That's okay, there's nothing wrong with that. But for when we want to do manipulation of data, it's a lot easier if we actually do that for the data types that are already in Clojure. So if we, rather than have these angle brackets, we can just have a vector, and rather than the div tag, we still use a div name, but we just make that a keyword. And that should be H2, but there we go. We just use a keyword and put that as the first value in the vector. And then, so here we've got, for this heading 2, we use that as the keyword, and then we've got the string as the value that's going to be inside that H2 tag. So this would be the equivalent of H2 just double triangle. Yeah, so that would be the kind of same as these two bits of that. So that would just be, this would actually just generate this as output, which just gets puts here in the result. Let's keep that for now. And then we've got an input of type range. So again, this is just normal HTML, but written in Clojure style. And then when we do some inputs, so when we use the mouse, we're actually going to reset the shape size. So we've actually got a little function that's going to call. So when we move this, a function is going to call and update, or in fact, just reset the shape size. So whatever we set this value to on this input, so at the moment it's set to 16 because that's where it's getting the shape size from, and yeah, it's going to update that value. It's just using the current target, which is the target of the input, and getting the value. So these dot dash names are the names that are used in the kind of JavaScript kind of world that we're working in, and we just use those to to be able to update and set the values when we move the input. So if we move this input, we can see we can change it, and 16 was it? And we can move the numbers up. As we move the number, as we move the input, this def cell is also being updated again because this is a cell, so it will replace the value of shape size with whatever the current value is when we call this reset. So in fact, this def cell is kind of listening. This cell is listening to that value each time and showing it as well. So we get some interactive stuff. Any questions so far? No. That's what we got next. Okay, I'm going to have a quick break and look at the how, kind of give you a bit more of like a detailed idea about how this is working with a Clojure atom example. So I'm going to switch over to my editor. And there's a link in the description with all this code in. There's a GitHub gist that has all this code in. You can see, let's make that a little bit bigger for everybody's read. This is just a simple example using the Clojure atom. So this is built into the Clojure language, and an atom allows us to change the states of something, change the value of something without worrying about it affecting other things, without any conflicts. So if two things are trying to change a value, the same value at the same time, and it's an atom, then it's going to so the atom is going to manage that. So only one thread, only one thing can change the atom at a particular point in time. So let's have a look at this example. So here we've got a book, and the book is represented as a map. And the map just has like title, author, and some tags to kind of define the topics that the book covers. So it's a simple kind of, this is all just standard Clojure stuff. So we're defining a name for this book, so we can refer to the map by book Clojure state changes. If we do make some changes to this book, then it's going to behave just like a normal map does in Clojure. So let's evaluate this, and so if we can evaluate and get the book, and it's got the title and the name. Although my name is only J, it's only put the initial in as my name, so I might want to change that at the moment. If we wanted to change that, we can just use the assoc in, so associate in. So we can associate a change into the map that is the book Clojure state change. And because it's a nested change we want to make a change to the author, but specifically the name of the author, and then specifically the first name of the author. So rather than just doing assoc by itself, we can do assoc in, and then we can specify the map and then the path to the value that we want to associate in instead of the value that's already there, and that value is John. So if I evaluate this now, and then we can see, so this is a comment of the result. Now we can see that the author name, the first name is now John, so that's great. But what happens if we go back and evaluate this? We can see that the first name is actually still J. So this is perfectly normal. This is how Clojure works. So what we're returning when we do the assoc in is a copy of the map with the changes that we've made. And so the original map, the original book has not changed. So this allows us to do very safe programming, because we can just pass around a data structure. And if we want to keep the changes, then we'll pass that back as return results to another function. If we don't need to keep the changes, we can just discard them. They'll just go out of scope. And the original kind of values are still there, remaining unchanged. If we wanted to share those changes across a number of functions, again, we could pass the normally would pass the information around, but especially if it's a UI change, you might want to put something in an atom because you don't want to keep all the changes forever and ever. You don't want to persist them. So you can actually use something called atom to, again, like we did with cell, we can wrap the book that we've defined here. So we've got the book we've defined here. We can wrap that in an atom. So we can just call the atom function, and it will wrap the book closure state change book in an atom, and then we can change it. So when we do change it, it will change the value. So we can see that here. So if we evaluate this, so we're not changing the book yet. The book will still be exactly the same as it was before. So, oops. Yeah, so the first name is still J. And we can see that, actually, yeah, if we can see that a bit more clearly if we do, we just get the author value. So we just get the author bit of the map. Yeah, and we can see the name and first name is still J. So we haven't changed anything yet, but we can use swap and reset as we did before in the cell. We can use that to actually make a change. So we're going to call swap. We're going to pass in the mutable book that we've used. So this is the atom we've wrapped around the book. We're still calling the same function. We're still calling associate in, and we're using the same path, and we're using the same the same value to change the name. And so if we run this, and we'll get the answer as a comment. And so again, ASOC has changed the author name first to John, and this is so that's been updated. But if we go in and look at author, well, let's just do this. So we can get the value of the mutable book by using this @ sign in front of it. If we put something into a reference, if we put something into an atom, then we can't just use mutable book. We have to dereference it first. So this is what this @ sign is doing. Essentially, it is a shorthand for doing deref function, which will again allows you to access atoms and all the other kind of software transactional memory things like refs and agents, so on. But Atom is the main one that most people use. There's also features and promises for doing kind of asynchronous development as well. But essentially, it's just going to return what's inside the atom, so the current value of the atom. So if we did deref mutable book, so then it's getting, but now it's still getting John. So the author name John, first is still John. So it's actually been changed in the atom. So the atom has a new version of the map, and here again. Yeah. So it's now first. If we go and look back at the book, then we can see that the book is still the same first name. So we haven't actually changed anything. If we wanted to reset something, we can, again, we saw in the cell that we can reset values. That's what we were doing with the slider. If we reset the value, then it goes back to J. Oops. And we can see that the mutable book is. Oops. Let's just double check that. Yeah, so the mutable book is now back to J. So whatever changes you make with swap are available and kind of accessible through the atom. So the atom is managing mutable state changes, but the thing that's actually inside the atom, the map itself, is still a mutable value. The book itself, the original definition of the book, has not changed. So whenever we call this book, it's always going to be the same book. It's always going to have that, no matter what we do inside the atom. All we're doing, we can consider the atom as a box that we're putting things into, and whenever we change the box, we're not changing the thing that's in the box. We're just changing the contents of the box itself. So if we put a human in the box and then decided to change, decided to put a different human in the box, we haven't affected the human by putting him in the box. We actually just put in, we're just swapping in and swapping out the values that are inside that box each time. And yeah, it's a nice way to kind of manage that state change without having to worry about locking values or different threads trying to access the same thing at the same time. So I hope that gives you a bit of an explanation about what atoms are, and we'll do a look at atom broadcast some in the very near future, I think, as well. It's quite a good thing to talk about. And atoms are quite often used in user interfaces. So if you're building a website, using anything like reagent or reframe, then you'll be using an atom to kind of manage the application state. So they use that to if some piece of data changes, then if that's managed by an atom, then all of the relevant components in your user interface can be updated very easily just by watching the atom. And if there's a change, so if you change the title, you change a component in the like some data that a component uses in the UI, then that will be updated. And there's you can see that example. There's an example in the Practicalli Clojure scripts. So there we go. Practical Tic Tac Toe. So here we're using an atom with the game board, and it's here we go. Oops. I got that. Yeah. So we're using an atom in the game board, and to manage the state. So whenever we put the board of the Tic Tac Toe in there and into the atom, and then whenever we make changes to that to the board, then the actual visual board gets updated and rendered when the contents of the atom changes. So when we see this app state change, then this tic-tac-toe game gets updated, gets redrawn on the page, and it's a nice way for us to whenever we click on something, then that changes the app state, and then that changes that gets the component that draws the board to update and redraw the board with the move, and that all happens pretty instantaneously. So we get a nice tic-tac-toe game just by using an agent to manage the underlying positions in the board, and whenever we click on something, that's an event that will update the atom or the contents of the atom and trigger a redrawing of the board. Any questions on that? Nope, no questions. Okie dokie. I'll put a link to that into the board there as well. What are we doing? Oh yeah, here we go. So that kind of hopefully gives you some insight into how the cell is working. So we'll see. So this reset bang, this reset exclamation mark function is a normal Clojure function that's updating the cell, updating the contents of the cell, basically resetting the cell to whatever, resetting the cell that is called shape size. And we're basically just pulling from the current target the value as an integer. So it's basically getting the value of this slider as an integer, and it's going to reset this def cell value to whatever this slider is whenever we move it. And you can see that in the top there as this number changes. So it's quite a nice way to get some interactive nature into your code. Okay, let's see what else we can do. What we got there? So here we're like we did with the book. Actually, it's a very similar example. So we've got some state that's wrapping a map, and we've got a size, and we've got a color range, I guess, and then we're going to use the cell to draw. Oh, okay, yes, we're going to use a cell to create a circle based on the sum state size, and it's going to colorize basically by getting the first from sum state colors. And then we're also adding a listener function here. So this will listen specifically for clicks, mouse clicks. So whenever we click on the cell, then it's going to change. Basically going to swap the value that are in the cells, in this def cell, in this sum state. It's going to associate the size. So it's going to increase the size by 20 and then create a associate the size by adding 20 with some random int. So it's got some randomness to it. And you can see up here what the new size is. And then we're using for it's changing colors because we're using this shuffle function from Clojure. So it's basically just like you're shuffling some cards in a card game. You're just going to shuffle the values from specifically from sum state colors. So this sum state is a map, and we're going to pull out the values of that map that colors points to. So this shuffle is going to shuffle the values that are in this collection, in this vector. And that is associating, so we're associating the size with this new size and the colors with the result of shuffling the colors that are in the state. So we've got the 3 different colors, and we're just basically cycling through them. I guess you could have change this to red. Red, yellow, green. Did red, yellow, green. Then we'd have like a very dangerous traffic light because it doesn't quite go into the right order that it's supposed to do. But you could write some logic around that. So instead of just doing a simple shuffle, you could set it, and you could actually just create an animated set of traffic lights here where you have all three colors, and you could set the opacity of the colors. So when the color wasn't lighted, you could reduce the opacity to a very low number, and when the colors are on, when the lights are on, you can just basically crank up the opacity of the color to close to 100 or 100, and create a nice kind of animated traffic lights. I'll put that down as a nice little exercise for slightly more advanced people doing ClojureBridge, I think. What we got here, so we're using some layers. This is just simple layers, just using Pumpkin. It'd be quite interesting to, you could animate the eyes and maybe animate the mouth as well. What we might do is you could create a specific, so instead of having all these unlabeled positions, you could have specific things for mouth and eyes and get them to move in coordinated ways as well. This code is a bit harder to read because which are the, so I guess, I mean, the circle is fairly obvious because it's the circle that's the whole pumpkin. But then you've got like triangles are the eyes, but which is the left eye and which is the right eye. You can probably guess that must be the left one and that's the right one, but they don't have names. So you could actually define these as individual items and then combine them together to be the pumpkin face and then animate the individual parts of the pumpkin. That might be quite cool. Take color names. Here's just some nice kind of some nice Clojure examples of getting the values of blue. I think we've seen that before actually, but creating a color picker would be quite cool. So what we got here, see what this looks like before we do that. Okay, so this again is more sliders. So here we've got we've got a color picker which shows us what the color is, and then if we look at that, we can see the red, green, blue thing there. We could add something that looks at this map and sees whether that matches a particular color. So we could actually just replace it with a name. So we could actually use this to find color names for us as well. Let's see. And then this one is this is quite cool. It's like this is like a contribution from one of the ClojureBridge Berlin attendees. And it's a nice flower. So we defined a flower here, and then we're also putting it into a cell. And what does that do? There we go. Oh, cool. So animated a flower. So we've got a flower here, and it's just basically animating the actual petals of the flower. You can maybe do like a smiley face in there that like changes with the animation as well. And this is just a matter of drawing a whole bunch of circles in the right places. And the rectangle, I guess, is, I'm not sure. Oh, the rectangle is just the around. Oh, the rectangle is the stalk. Oh, there we go, yes. And it's just using round-end leaves, and the leaves are, it's very, very interesting color choices for the leaves. And it's just cycling through these different colors for each of the leaves on layers, and might be quite nice if you did it like round robin as well. So like they kind of animated. So you got the top one changes color, and then the next one changes to a similar color, and then they all go to one color, and then they start merging into another, and then another, and another. That might be quite cool. And somebody spent a bit of time figuring out how to draw one of the famous landmarks in Berlin, which is one of the towers that are in there. Oh, that's a lot of code in there. Again, that's definitely worth kind of breaking that up into different sections and make it easier. was working. Oh, is it all the way back up there again? Oh yeah, there you go. Oh, that's quite clever. That's quite nice. That must have taken a bit of time to work out how to actually do it, because it's quite intricate, lots of little pieces to there as well. But that's quite nice. So it's quite fun to see what you can do. Let's just go and have a look at cells. So there is a specific thing on cells, but I think this we've covered most of the things here. So setting an interval, and we can also do counters on there as well. Oh, we haven't defined what counter is. There we go. What's that? Oh yes. So we define a counter of we define a counter. We can see the counters. So we can see the interval in action. So we can do an interval with a value and also give it a function as well. So what is it doing? So it's going to increment a number every second, and we're seeing the result there of that. Does this work now? There we go. And this is doing the same thing. This is using the counter, but rather than doing just updating it by 1 each time, we're updating it by 10. You can see we run these at the same time because they're of an order of 10 difference. And just like we can dereference the atom, we can dereference the counter as well. So we can call in the counter value at any particular time. We can interconnect cells as well. So again, if we have like different cells with different, we can go and reference them. What's this doing? Okay. So we're generating just some random numbers at every 0.2 of a second. And we're just going to get, so that's one cell. So this one cell is just generating numbers. And then we create another cell that will update it, but just taking the last 10 of those numbers that are generated. So here it's pulling up it's counting up, so it's grabbing the numbers from this random number, and then it's just keeping the first 10 of that. So we construct a list, a sequence, using random number and self, and it is going to so it's passing that back to itself, and it is just going to take the first 10. So when it first runs, then it's it just has one value, and then it keeps adding them till it gets to 10, but then it doesn't add the 11th one because it's dropping them each time. It's only going to see the first 10 of those values. So we can see that once we've got up to 10 values, then it stays at that size as well. So it's kind of nice way to kind of animate something like a snake trail kind of thing, and actually yes, for the animating of the leaves in a kind of a continuous kind of change as we kind of go clockwise around the leaves of a flower. You could use this counter to basically gradually change the colors of this thing by just we start off with 1, and then 1 propagates through there, and then once 1's got to 10, then we start moving on to 15 and 35, and every kind of different value set kind of gradually changes the color of the flower each time as well. That'd be quite cool. Let's just put a note on that as well. So that's where we go. Yeah. So then it's just a description of how it works. Yeah, I suppose if you took 25. different number, then it's obviously going to show you the number. So this is quite interesting because it'll only show you so many of the values by initially. So if I did like 250,000, that would possibly slow the whole thing down, or like 250 million. That might be it. So, and obviously it would just fill up the entire page. So whenever you're doing something over a certain size, then you get little dot 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 to expand the results if it's like a collection. You get the same thing in most Clojure editors as well. We can do some kind of logic around cells as well. So if we set this toggle to true, and so we're drawing so we're using if macro. So if toggle, which is the def cell that we're referencing, if that's true, then we'll do the first thing. If otherwise it's false, then we can do the next thing. So again, we can use this to do some animations. If we do false in here, and then we evaluate, and then evaluate this again. So if we put this conditional into a cell, then it will. There we go. It will animate based on the changes we make in. And we could have like a button that was like true and false here. So if we did true again, and evaluate that. So that's now true, which hasn't changed this square because it's not in the cell, but it's changed this square to a circle because it is in a cell. And so that's quite interesting. And then there's listen we've seen where we're listening for mouse events as well. And anything else we've got? Anything else we've missed? No, that's it. There was some interesting examples. Where did we get to? What was it on? Oh yeah, there we go. So there's some interesting constraints I found around cells. So here we're defining a hollow circle. So we're basically just defining a circle of a certain size, which we're going to call 50. We're going to call hollow circle 50 from here. But there's not going to be any fill in there. So fill is the normal color of the circle or square. So you can have fill and stroke. And stroke is it's kind of the border. So you can have like a different border around an object. The only thing is that at the moment, when you do a stroke, it actually just gets outside of the boundary of the cell itself. So you actually get a funny kind of drawing of that. And we can also use the boundary of the cell to do some interesting effects as well. So this is just a square, but because some of the square is going outside of the boundary of the cell, then it looks like it's changing shape. So it's actually a very quick, it's a very hacky way of looking like it's actually doing some animation. But actually, we just the scope of our cell is just kind of cutting off the shape of our square. So we're just rotating this square clockwise, but the corners are getting sliced off as we go around. So when it's there, it's fine, but at the other points, it's actually getting the corners chopped off. And there's an example where we're just changing the color. And here we're just, we can see the color changes going. We can see like color changes going through there, and we could set up a listener to see what those color changes were. So there's some interesting, probably unintended effects from this like kind of cell, but we could use this cell boundary to do some interesting animation as well. If you wanted to avoid this issue, I guess just positioning the cell, positioning the shape that we're using to be more inside the actual cell itself. So we would have to do, I mean, I guess we could do a layer where we have a a shape, just a square. We can just create a rectangle that's completely transparent, zero opacity, to be our kind of borders of the cell, and we just make sure that the shapes that we're drawing with full opacity that we can see are within the boundaries of that larger rectangle. And that would help avoid this issue if we didn't want it to happen as well. There is also some info on this idea of data flow, but some of the examples are not quite working yet, so I'm not quite sure what's going on there. So I'm going to leave that for another time, but feel free to go and have a look at that. It's just Maria.cloud / data -flow. And allows you to grab data from the web and do stuff there. I think, does this work? I think some of this works, but some of the examples are not working as well. So here it's pulling out my geographical location there. Yeah, some of the things are not quite working, so I'm not quite sure what's going on there. But I'll have a look, see if we can fix some of those. Cool. Okay, well, that was it. And there aren't any questions I can see. No. So I will leave it there and just thank you very much for listening. If you want to come to the ClojureBridge, next ClojureBridge event, we've got an event coming up on the 10th, 11th of May. Apologies, these are American dates. It's an American website we've been using for the registration. So this is the 10th of May and the 11th of May. And you can sign up as a student. And we've got quite a lot of people coming. So we're trying to get a nice balance between coaches and students. So we've got like every student that comes along will get a coach. And yeah, it's a good fun day to spend all Saturday learning how to do programming, learning how to play around with Clojure, and you can do some Mariacloud, or you can do you can build an application if you want to as well. We also have some coding challenges you can actually do to help you get more comfortable with solving things in Clojure as well. So we cater for absolute beginners, with some people with little coding experience and then some experience coding. And you can just build an app or a game or a website just by sitting down with the coach all day. Okay, thank you very much for listening and see you again next time. Thanks, bye-bye. Bye-bye.